All right, next up we are going to take a look at the proof of Theorem 2.1.3 and a couple of other related theorems. All right, so Theorem 2.1.3 says that if a graph G is critical with chromatic number 4, then the degree of each vertex is at least 3. All right, so this theorem basically tells us a little bit more about the structure of a critical graph, at least for um, chromatic number 4, right? It tells us that there's got to be quite a few edges in there, right? The degree of each vertex is at least 3, okay? Uh, so, um, so you can't have any, end vertices in there are isolated. We already know that, right? Because critical graph is connected. So you have to have, quite a few edges in there. The degrees have to be high for the vertices in the critical graph. All right, so I already got this proof written out to try and speed it up a little bit. And so we're going to prove this by contradiction, right? So we can assume the hypothesis is true, right? G is a critical graph of chromatic number 4, and then the opposite of the conclusion, right? That the degree, it is not the case, right? That the degree of each vertex is at least 3. So if that's not true, right, you're going to have a vertex with degree 2 or less in there, all right? So that's what we get to assume. So suppose there exists a critical graph G with chromatic number 4 and a vertex V with degree less than or equal to 2. Okay, so that's what we're allowed to assume. So what we're going to do, right, is remove that vertex V, right? And since G is critical, that means that the chromatic number, right, of this subgraph, it is a proper subgraph, right, because it is missing the vertex V, and so therefore its chromatic number has to be less than the chromatic number of the graph G. So that means that the chromatic number of G minus V, right, has to be 3 or less. So that means we can color G minus V with 3 colors, okay? All right, and possibly less, but that's all we need, right, is 3. All right, and we know that the degree of this vertex V is less than or equal to 2, right? So that means that V is adjacent to at most 2 other vertices of G, right? Okay. So we've just colored all of the other vertices, right, with 3 colors. So there's 3 colors and only at most 2 other vertices are adjacent to G. So that leaves one of the colors out, right? And so that means that there's got to be one of the 3 colors, possibly more, but all we need is one, right, of the 3 colors that's not used to color the vertices adjacent to V. So it would kind of look like this situation, right? Here is V, and I didn't color V because remember we popped that one off, right? And then we color the subgraph with 3 colors. All right, and then so here the colors are red, green, and blue, right? But remember, V is only adjacent to at 2 of those at most, right? So that means we couldn't use this green color, right? We couldn't use the red color, but we have one color left that is possible to use, and so that's what we would do. And so in this case, we would color that vertex blue right here, right? Okay. All right, so now just think about what we've done. We have assigned a color to every vertex of G, right? Before, the coloring that we started with was only for G minus V, right? But we colored the vertex V with one of the colors that was used already here, right? So all of the vertices of G have been colored, and you're only using 3 colors to do it, right? And so that is a contradiction. It's to the fact that the chromatic number of G is equal to 4, right? Remember, if the chromatic number is 4, that means that the graph can be colored with 4 vertices, and it cannot be colored with 3 or less, okay? And we've just done it. So that is a contradiction, right? So therefore, the conclusion, right, of our theorem must be true, okay? All right, so that is the proof of that. Okay. If you go back and look at some of the example that we talked about, critical subgraphs, right? We said that every complete graph is critical, right, in the previous video, or one of the previous videos. And so if you look, right, this graph is critical, and the chromatic number is 5. And if you look at the degree of each vertex, right, it's at least 4. You can see, right? In fact, for the complete graph, the degree of every vertex is 4. Whereas if we had this other critical graph here, we said that this graph was not critical, right? The chromatic number is 2 or 3, right? And so that would mean that if it was critical, then every vertex would have at least degree 2 in here, and it does not, okay? I guess I am jumping a little bit ahead of myself, right, into the next theorem after that. We proved it actually only for chromatic number 4, but right, the theorem is true for if G is critical with chromatic number K, then the degree of each vertex is at least K minus 1. And it follows exactly along the same lines of the proof that we just did. Instead of using 4, you're going to use K, right? And then instead of 3, you're going to use K minus 1. So it works exactly the same way as before, okay? And so I should have mentioned that before I looked at those other examples. So. Okay, that leaves us one last theorem that we're going to cover in this section, and that is this theorem 2.14. It says if G is a critical graph with vertices, with P vertices and Q edges, and G has chromatic number K, then the relation K minus 1 times P is less than or equal to 2K holds. All right, and so that goes back to the fact that if you sum the degrees, right, if I have a graph G with P vertices and Q edges, right, then the sum of the vertices D1 plus D2 plus D sub P is equal to 2 times Q. Okay. So if you add up the degrees, right, this is what theorem from chapter 1. If you add up the sum of the degrees, or the sum of the degrees is equal to twice the number of edges, right? And so we know that this graph G is critical, right? So that means that the degree is at least K minus 1, right? 1 less than the chromatic number, all right? So D1 is greater than K minus 1, right? D2 is greater than or equal to K minus 1, right? And all the way out to D sub P, all of those, right? So we can replace all of those, right, by K minus 1. So D1 plus D2 all of that, right, is greater than or equal to K minus 1. So K minus 1, right? Because D1 is, and K D2, right? It's greater than or equal to K minus 1. All the way out to D sub P, right? Greater than K minus 1, like so. All right, and then counting up how many you have of those, right, is P, right? Oops, I didn't draw that far enough. Okay, so I have P copies, right, of K minus 1, right? And so that means that this is equal to keep fumbling around with the iPad here. Okay, so that means that this is equal to P times K minus 1. Okay. All right, and so just putting all of this together, right, is that P times K minus 1. All right, I think we have it the other way around here, but doesn't matter. K minus 1 times P. This. That is equal to this sum, which is less than or equal to the sum of the degrees, right? And the sum of the degrees is equal to 2q, right? So that in turn says that P times K minus 1 is less than or equal to this, which is happens to be equal to this, right? And so that gets us what we want here. All right, and so another way of looking at this equation, if I divide both sides by P, right, I get 2q over P, right? And if you look at what 2q over P is, that is the same as the average degree. You can see that that's true because just go back up here to that very first equation. And if I divide both sides of this by P, right, it's really easy to see that this is the average degree because I'm adding up the degrees and dividing by how many I've got. That's the average, right? So 2q over P is the average degree. So another way, another corollary, right, of this is that the average degree, right, of a critical graph with chromatic number K, right, is greater than or equal to K minus 1. All right, and so that is it on this video.